Until this point in the module, we have described how the WWC calculates effect sizes for individual level assignment studies with continuous measures. We now will turn our attention to how the WWC conducts these calculations for cluster level assignment studies with continuous measures. The statistical considerations for effect size estimation are a bit more complex for cluster level assignment studies. Cluster level assignment designs often yield more uncertainty or larger standard errors for intervention effect estimates. This is because the total variability in cluster level assignment studies consists of between cluster variability and within cluster variability. The WWC's effect size calculations use that total variability to standardize the effect size metric. By using the total variability as the standardizer, the WWC can calculate effect sizes from cluster level assignment designs that are comparable with effect sizes from individual level assignment designs conducted in several sites. For instance, a study with 100 students that are assigned to conditions individually typically will have more power than a study with 100 students in 10 classrooms with assignment to conditions occurring at the classroom level. The effect size will need to account for the variability between classrooms as well as between students. How the WWC calculates effect sizes from cluster-level assignment designs will of course depend on whether the outcome or characteristic of interest was measured continuously or dichotomously, but the type of calculations used also will depend on whether the study authors report or have access to statistical information at the individual level. It also will depend on whether the authors corrected their analyses for the clustered study design. And finally, the calculations will depend on whether the study design requires baseline adjustment to meet WWC standards. A common way to compute effect sizes from cluster-level assignment studies is by using an estimate of the unstandardized mean difference, B, and the pooled individual level standard deviation, SDP. The information needed for this effect size typically will be model components from a regression analysis that accounts for clustering. In the equations shown here, N is the total number of individuals, M is the total number of clusters in the study, and rho ICC is the intra-class correlation that represents the degree of clustering. This formula is appropriate for both unadjusted and covariate-adjusted estimates of the mean difference B. This formula is similar to the Hedges G formula for individual level assignment, but it adds a new bias correction term, the square root of gamma. Think of this term as an adjustment factor for small numbers of clusters. Although the value is usually small, this adjustment is needed to yield approximately unbiased estimates of the population effect size, especially for studies with few clusters. Importantly, this formula assumes that the study authors analyzed individual level data or otherwise had access to individual level standard deviations, which are necessary for computing the pooled standard deviation. The WWC will compute covariate-adjusted standard errors of the effect size for cluster-level assignment studies. One complication is whether the study author's analysis model appropriately accounted for clustering, which substantially can change the author-reported standard errors. Study authors can account for clustering in multiple acceptable ways. For instance, they can include random effects at the unit of assignment in a multi-level model, which are sometimes also called hierarchical linear models or mixed effects models. Study authors could also conduct a single-level ordinary least squares regression model and then adjust the standard errors at the unit of assignment level using cluster-robust standard errors. Either of these approaches can yield regression coefficient standard errors that account for clustering. If the study authors reported a cluster-correlated standard error for the unstandardized mean difference, or SECCB, then the WWC will compute the effect size standard error using typical information required to calculate effect sizes in these scenarios, plus the cluster-corrected standard error. But sometimes the authors of cluster-level assignment studies do not account for the clustering of the design, even though they should. For example, researchers might estimate an ordinary least squares regression model without adjusting the standard errors for clustering. The standard errors from such models cannot be substituted into the equations we've discussed so far, because frequently the standard error will be too small. Fortunately, the WWC can compute the effect sizes standard error under different scenarios. For instance, the WWC can compute the effect size standard error if the study authors reported an uncorrected standard error, or SEUCB, for the unstandardized mean difference using the first formula. Alternately, if a study reports the multiple correlation, or R-squared, from a single level model, such as an ordinary least squares regression, or an analysis of covariance, but they do not report the regression coefficient standard error, the WWC can compute the covariate-adjusted standard error using the second formula. These formulas are similar to those used in the case of individual level assignment studies, but they include the design effect to adjust for clustering. When calculating the design effect, the WWC makes assumptions regarding the value of the intra-class correlation, or ICC, based on the type of outcome measure being used. Assumptions about the ICC are detailed in Appendix E. Recall that the WWC always prefers to calculate effect sizes and their standard errors from covariate-adjusted analyses, but some studies may only conduct unadjusted analyses. For unadjusted analyses, the WWC can calculate the effect size and its standard error using the following formula. This formula is appropriate regardless of whether the study author's analysis accounted for clustering. As before, the WWC makes assumptions regarding the value of the ICC based on the type of outcome measure. The formulas described previously apply to scenarios in which study authors analyzed individual level data or otherwise had access to individual level standard deviations. As we discussed in the introduction of this module, there are scenarios where authors of cluster-level assignment studies may not have access to individual level data and instead only have access to cluster-level data. For instance, a researcher may have access to school-level means available in a public dataset, but may not have access to individual-level student data. Here, we show how the WWC calculates a Hedges GFX size for cluster-level assignment studies that only have cluster-level data. This is similar to the effect size for individual-level data, except that the mean difference and standard deviations are at the cluster level instead of the individual level. The right half of the equation is a multiplicative factor that shrinks the effect size proportionally to the ICC. Here we show how the WWC calculates the standard error of the effect size for cluster-level assignment studies that only have cluster-level data. The calculations are different depending on whether the authors reported unadjusted or covariate-adjusted analyses. As with the individual level case, reviewers typically do not need additional information for the unadjusted analysis, but will need the standard error of the cluster-level unstandardized impact to calculate the standard error of the effect. Finally, it is worth noting that there are additional extensions to some of these formulas for cluster-level assignment designs. such as using the total standard deviation or gain score standard deviation as previously described. Please see Appendix E in the handbook for additional details around these other extensions. In the next chapter of this module, we briefly will discuss some details around studies with dichotomous outcome measures and then move on to knowledge checks before wrapping up the module.